when we did this, our calorimetry is just a Yeti cup. And in fact, no one puts the top on the Yeti cup. So is it really a closed system? People on chat, is this a closed system? If we just have an open Yeti cup? No, it's not a closed system. So we have heat loss that we just ignored as physicists. Well, because for us, it's just systematic error. So what if I add a heat loss, which was originally 0, and now I'm going to add a heat loss and rerun the code. And when I rerun the code with a heat loss of 6 joules, I'm now going to have a percent error of 31, which means 6 joules now I've modeled have left the Yeti cup. Well, it turns out it's a little bit more than 6. So play around with this value of a heat loss and keep playing with it till you're around 0% error. What do people get at? What is their heat loss such that they see pretty close to 0% error? This might take a couple minutes and feel free to ask. Remember, you're going to have to press play on the first one and then play on the second one. So you're going to have to run it twice, or run the top one and then run the bottom one. So Margaret, what are you getting? Can you come off mute?
Yeah, I tried 10 and I think I got a 6% error, and that was the lowest I've, or no, wait.
Okay, try 11. What do you get with 11?
Okay, one sec. With 11, I get a 0.57% error.
Yay, and people are saying, oh, try 11.5. So let's all try 11.5. So somewhere between 11 and 11.5 within the random number generator, we're getting pretty close to 0%. So Margaret, how would you put that into words if you were to talk to the people in the table? Do you know how you might say that? Like in terms of systematic error, maybe I shouldn't call you, put you on the spot. Just open it up. Anyone, how would you describe what we just did to explain why our percent error was so big? Because initially, the model that you use in lab today, that everyone's using in lab, they're going to have a high percent error. And we're okay with it. But what can you guys do using this code to help them understand how to explain their percent error being so high? Anyone want to take a stab at it?
Well, I can try. If you don't account for any heat loss, like if you say that the heat loss is going to be 0 joules, then your value is going to be far off from the actual like literature value, which that makes the percent error really high. So when you account for that like heat loss and error, then it makes it go down a lot.
Exactly, bingo. So when we graph it, our theoretical value is 385 for copper. So let's just think about this graphically, because we did those worksheets, right, on comparison based. So 385 is right here. Can you guys see my cursor? Yes?
Yep. Yes, ma'am.
So is this 1 standard deviation away from where the mean is that we have? Because our mean for all of these values is right here. Does that look like it's 1 standard deviation away?
No.
No.
Oh, really? Well, maybe I'm saying this wrong. So if our mean is here, plus or minus 1 standard deviation is right here, correct? Or let me ask. Maybe I can ask. So if you were to look at this graph, which is every single specific heat value we have, because remember, we have 1,000 data points. So in my graph, 194 of the data points is around here. 182 of that 1,000 is here, and 186 are here. So between here and here, I have 68% of all my data, correct? All my generated data. Does that make sense? I need to actually talk to someone. Does anyone, let's see, who can? George, can you come off?
Sure.
Okay, great. So one standard deviation, if you were to just look at this distribution, can you talk to me about where you think one standard deviation might be? Just
So like,
approximate.
if there's 1,000 data points, I think one standard deviation was 68% of the distribution. So that would be, it would like, you would have to, I guess, count the frequency, and you would have to like count from the middle 340 from each side, because 340 on the right of the mean and 340 on the left of the mean would be 680, which is 68%. So that's where your one standard deviation.
So it's 117, 134, 182, 186, and 194. Is that 600?
So you have what was it? 182, 194. Yeah, that's roughly 600.
Exactly. So right in here is one standard deviation to the left and right of the mean, correct?
Yeah, that sounds good.
Okay, but we actually calculated our value to be 766. So our actual mean is right here, correct?
Right.
But our theoretical value for copper is 385. Our theoretical value is way over here. Is this outside one standard deviation for sure?
Yeah.
So there's definitely systematic error, correct?
Yes.
So we would expect, given randomly generated data, that even if they were picture perfect in their lab, everything was beautiful. They did their procedures correctly. They used their tools correctly. They had a little bit of a process error, and they were perfect human beings in this lab, perfect scientists. We expect a systematic error because of the model we used, correct?
Yes.
So this is not human error. There's no human error in here. The only thing is because we can't account for the heat loss. Does that make sense now? How to go about and see these, how do you say this? So many times in lab, people want to say, well, you know, we did this, we did this, we did this, and therefore, you know, it must have been a problem with the way in which our, you know, the way in which we carried the Yeti cup from the hot water to our actual measure sensor. It's like, no, actually, you could do that all day long. I don't care. You can do that from nighttime to morning. You can do that in the summer and winter. You're fundamentally going to have a problem. And the reason is because we can't actually measure this heat loss. It was the same thing with the ball drop. You can assume that there's no friction and the ball drops really fast because there's very little air friction. But it turns out the air friction is still significant. And it just depends on how long they kept the Yeti cup before they reached equilibrium as to whether or not this was a big effect or a small effect. And likewise with the friction one, whether it's a bigger effect or a small effect, all depended on the surface area of the object they dropped, and whether or not it reached terminal velocity when they did drop it. So likewise in here, we expect in this lab to see systematic error, and it's not a problem for physicists. And this, I think, helps to be able to make explicit and visible the types of things we're talking about when we talk about the difference between random error and systematic error. So now you can use this code if you want. You can actually play around with this number and talk about that, especially for the person who has 2 people in the lab today and it's isolated. They're going to think you're brilliant to be able to describe that. Who is it that's isolated?
That's me.
Oh, it's you. So if you can just grab their temperature data in mass and say, oh, I don't care, just approximate it. You're going to drive them crazy. They're going to give you 4 digits. It doesn't matter. Just take their data and generate it, and then just change that heat loss, and you're going to be able to give that to them. That makes sense?
Sounds good.
Yeah, they're going to think this is awesome. Well, based on the other people in the lab, they are. So what does that mean? Well, if you want to read all of the details about how you interpret setting up the mean and the standard deviation. The mean is also approximately what data they took. And then the standard deviation is the actual sensor uncertainty. And usually you add a little bit more for process error, not for mass. There's really no addition or subtraction of the masses they use. Mass isn't just falling off these objects or adding to these objects. So there's not much standard deviation to mass, but temperature, there's a lot.